Great. Excellent. Okay, so tonight we are honored to have Professor Mark Kisin from Harvard University speaking in our seminar series on essential dimension via prismatic cohomology. Professor Kisin needs no introduction to number theories, but as is customary in our lecture series, I do a very brief introduction. Professor Kisin obtained his PhD in 1998 from Princeton University under the direction of Professor Nick Katz. And from 98 to 2001, he was at University of Sydney, then University of Munster, and after 6 years at the University of Chicago, where he was a professor, he moved to Harvard from 2009. Professor Kisin is very well known for those working in the areas Shimura varieties, p-adic Hodge theory, and p-adic cohomology theories. And he was an invited speaker in ICM 2010, and since 2012, he is a fellow of the American Mathematical Society. This is a very brief introduction. I know it doesn't do any justice to Professor Kisin, but anyways, that's customary for our lecture series. So let's welcome Professor Kisin to start his talk on essential dimension via prismatic cohomology.
Thank you very much, Ali. And I should say that when I arrived in the US for graduate school, just when I arrived at the airport before I even got to Princeton, I still remember I met Ali at the airport in New York. Okay, so right, so this talk will be is about some joint work with Benson Farb and Jesse Wilson, and it's really about a question which is very classical, which I'm going to explain in a second, which in some sense, if you look at the question, it looks like a question about maybe the topology, about complex algebraic varieties. And the interesting thing is that this question can be addressed with arithmetic methods. In fact, you can go further with arithmetic methods than people were able to do before. So let me first explain the kind of question we're going to consider. So let's suppose we have a variety x over k, over a field k, which I'm going to assume is algebraically closed. And so later we'll switch setups actually a little bit, but for now you can even consider the k as the complex numbers. Okay, and then what we want to do is we want to consider a covering and I'll give an example in a second. So in algebraic geometry, that's what you would call a finite étale map. And now the question that you want to ask is, when you have such a covering, so X is a variety, it has some dimension, right? You want to ask whether you can reduce this covering to a covering of something in smaller dimension, okay? So question, does F come from a covering in smaller dimension? And in fact, you're interested in this question only birationally. So that makes the question harder. So, let's be a little more precise. So i.e. we'll consider, let's consider U inside X open. So a non-empty open. And diagrams of the following form. So here we have my covering X prime, which I'm going to restrict to this open subset. And now I want to consider coverings y prime y such that this diagram is Cartesian, right? So x prime restricted to u is the Cartesian product. And there's an invariant, the central dimension of our covering is the smallest y. So I can take the minimum, let's say, over y and u, such that there's a diagram like this. Okay, so it's the smallest dimension such that our covering can be obtained by kind of pulling back, right? So like one way of making such coverings is to take, I could have a covering of curves, for example, and then I could have some very high dimensional variety mapping to my curve, and I can pull back the covering. But that covering, that pullback covering, is not really more interesting than the covering of curves, right? So we're interested in situations where actually that's what one is usually trying to prove, that you have a covering and that this essential dimension is just a dimension of x, right? That you can't get the covering from anything smaller. So F is called incompressible. Compressible if this essential dimension is equal to the dimension. Okay, are there any questions about that so far? Good. So let me just give a quick example. So as I said, this kind of question arose in very classical literature, even in the 19th century, when people like Kronecker and Klein, they were thinking about things like solutions of the quintic or solutions of the general nth degree polynomial, right? So let's consider the general degree n polynomial. So the a's you should think of as just variables. And then, how does dimension of y depend on u? No, so the thing is, if the idea is you fix u, right? We're going to allow u to be arbitrary, but imagine you fix u for a moment, then you can ask diagrams like this, look at diagrams like this, right? So the only point is there might not be a map from all of x to y, right? And you want y to be as small as possible. Does that answer the question? The dimension of y is whatever it is. It doesn't, I mean, if I have such a u, I can always replace it with a smaller u, for example. Okay, so let me look at this example. So let's think of these coordinates as living in affine n-1 space. The a's are just the coordinates there. And inside here, I have the discriminant locus. So that's the locus where the discriminant is 0, namely where this polynomial has a double root. And then we can take x to be an minus delta, or an minus 1, sorry. And then, so over this, if now I look at the solution of this polynomial, I get a cover whose Galois group is Sn. So this is an Sn cover. Okay, and it's a conjecture that the essential dimension of this guy is, I think, n-3. This is for n greater or equal to 4. Okay, that's actually still open. Actually, today we'll be interested in the following variant. This doesn't matter. You can just think of the original essential dimension question, but there's a kind of slightly stronger. Our results will actually be slightly stronger. They involve the following variant. So let's fix P a prime number, and then you can define what's called the P essential dimension. So it's denoted like this. And this is just, what you do is just defined in the same way as as the essential dimension, but you allow maps of degree prime to P. So this is finite degree prime to P. You can ignore this if you like. Okay, so all the results I'm going to state will be in terms of this invariant, but of course, obviously, if I get this invariant here is always less than or equal to the essential dimensions, right? Because I could certainly take W just to be X. So all the results I'm going to state apply kind of a fortiori to our original invariant, the essential dimension, but they'll be stated in this way. And I guess actually most of the things I'll be talking about, the result will be that the covering is P incompressible, which just means that the ED at P is equal to the dimension. Okay, so that of course implies the essential dimension is also the dimension. Yes.
So how does this definition of the essential dimension relate to the usual essential dimension, as in like algebraic groups?
Yeah, so right. So there's a more general definition, which I don't want to get into now, but let me like partially answer your question. So in this case, if you think about, for example, this example with the SN cover, because this is kind of the universal SN cover, right? This, whatever this is, it's also the essential dimension of this group SN. Okay, so does that kind of partly answer the question? And then you can imagine how it relates to more general definitions, right? So yes, you could also imagine that here we're doing this kind of for a covering. We're asking when does the covering come from something of smaller dimension, but you could do this for many other invariants. If you, instead of having like just a covering on X, you could have a tosser on X of some group or something like that. Yeah, so the answer is it's a special case. Okay, good. Thank you for the question. Good. So let me give another example, actually, and this is the kind of example that I'll be interested in, and the kind of example that more classical techniques had a difficulty with. So let's suppose I have A over C, an abelian variety. Okay. Now what I can do, I fix my prime P as before, okay? And I can, let's say of dimension G, sorry, so always the dimension of my abelian varieties will always be denoted G, if I forget in the future. And now let's just do the following thing. Let's consider, what's going on there? Let's consider the multiplication by P map on the abelian variety. And so I can think of the abelian variety as a cover of itself using this multiplication by P map. When I do that, just to kind of distinguish, I'm going to call the source of the map A prime. So A prime is again equal to A, okay? It's a covering of A itself, right? So this is a cover with group Z mod PZ to the 2G. Okay, and then you can ask, so that's an example of a covering. You can ask, what is the essential dimension or the P essential dimension of this covering? And so here's the theorem, which we show. At P, and therefore the essential dimension of this covering is equal to G, the dimension of the abelian variety, at least for P sufficiently large, okay? So then, as I say, in particular, if you're interested in the essential dimension itself, this is equal to G. So I think this kind of thing wasn't known. This was, even this very simple case was open. And the difficulty here for classical methods, I don't want to discuss the classical methods too much, but the difficulty here is that this is a variety which is proper. Okay, so basically the way people knew how to address this question was something called the fixed point method. And that means you have a covering, you study its ramification near a boundary point. But when your variety is proper, there is no boundary point. Okay. Okay, so this is really a consequence of the following. proposition. And now we see, I promised you that even though this is a question about complex algebraic varieties, that it's really based on arithmetic methods, okay, on arithmetic methods, okay? So now I'm going to formulate in things in a way which looks a little bit more arithmetic, okay? So now let's suppose I'm going to change notation. So now I'm going to assume A over K is an abelian variety over a number field. Okay, and P a prime. So you see here you have P sufficiently large, but actually this can be made a little bit more effective. And to make it more effective, the easiest way is to kind of explain what it says in the case of a number field. And so I'm going to assume that, first of all, P is at least G plus 2. And it's unramified in K. So that's a condition on P. And A has good reduction. At some prime P dividing P of K. I think this can also be a little bit weakened to A having semi-stable reduction, but that's not in the paper the way we wrote it. Okay, so then the statement is that the ED, if I look over the complex numbers now, the ED at the P essential dimension is equal to G. So the covering is P incompressible.
Sorry, there is a question also.
Yes.
What can I ask the
It's
does
okay.
P?
Forget about the question because Mark answered already.
Oh, no, that was the first
in
question.
a way.
Okay, thanks.
Oh.
Maybe I can, since you're interrupted, so why is it important that you work with C, complex numbers?
No, it's not important. I mean, you mean back here?
In the theorem.
In the theorem? Well, no. You see, in the theorem, I guess it's not important. It's not important. So in the beginning, I said K is just an algebraically closed field. I should have said of characteristic 0, actually, right? So the whole setup is, I won't go back and change it, but I should have said of characteristic 0. And here, this is just to get people thinking a little bit more like topologically. It's just to, I like to emphasize that this is just a statement about topological spaces. I mean, like complex geometry, and then it's proved by arithmetic methods. But that's only, the answer is it's only for effect. This is true over any algebraically closed field of characteristic 0.
And why characteristic matters? Can you explain maybe at some point?
You mean this? Why does this P matter? You mean
no,
why
why characteristic P, not why characteristic 0? Why can you work?
Oh, I won't explain that, I think. I don't think I even thought carefully about this. I mean, to me, maybe I did, but I forgot. To me, this is the most interesting question anyway. You mean, can you generalize this to characteristic P somehow? Is that right? Yeah, I have to. Maybe I thought about this at some point, but I don't remember. But
or what about characteristic prime to P? Does that kind of carry through?
Well, I'm going to explain the method. Okay, I should say that like the method doesn't obviously carry through to either of those cases. That doesn't mean that if you don't think about it for a little bit, that there won't be something. But I think characteristic prime to P is actually the most challenging.
Okay.
Anyway, you'll see the method, and then you can draw your own conclusions. Any other questions? All right. Let me just very quickly mention that this is actually a very special case of what we show. So there's a quite general results results for what are called p-homology covers. So I'll just give the following example. If you have a product of curves, let's say smooth, proper curves, then you can form the what's called the p-homology cover. Okay. So this is just the cover which corresponds to the maximal quotient of pi1 of x, which is an elementary abelian P group. Okay, and then the statement is again that this is P incompressible if P is sufficiently large in a way that can be made somewhat explicit. And this can also be applied to, by a more indirect argument, actually, to certain congruence covers. So I'm just going to write this kind of mnemonically and then say a little bit about this. So here X is now, I should have used a different symbol, but the only name you can have for a Hermitian symmetric domain is X. And this includes even the case, like the exceptional group case where it applies. So, so you can think, kind of a simple example is when you have here the moduli space of abelian varieties, then you have a covering, kind of the principal P congruence cover, the thing that corresponds to like the torsion, the P torsion in the universal abelian varieties. So that would be an example. So we show that's P incompressible by this method. But there are also more exotic cases that people couldn't do via other methods. Okay. All right. So now let's go back to our abelian variety. A over C or over an algebraically closed field. That's also fine. Okay. And let me explain the proof idea. So the idea is to use what are called characteristic classes of the covering. And this idea that goes actually back to Arnold. So let's, right, so we have our covering, a multiplication by P covering, and it has group Z mod PZ to the 2G. Let's call that group G, just for clarity. So G is the group of the covering. And so what I can do, let's see, I guess I can fit this in. So let me do the following thing. I can look at the maps from G is an elementary abelian P group. Actually, let me start a new page. Okay, so yeah, let me start a new page. I'm going to need a little bit more room. So it's an elementary abelian P group, so I can look at Homs from G into FP. And so this is 2G dimensional. I'm going to take the top G wedge. Okay, so this of course maps where I can to the same thing, but where I use the full fundamental group of A. Okay, and again, I can take the top G wedge. And of course, because of the way we've constructed G, this map is an isomorphism. Okay. And these maps, such maps, right? This is the same as the G wedge of the H1 of the abelian variety. Okay. And this is the same as HG. the abelian variety. And in this case, all the maps are isomorphisms. I want to emphasize, we could have done this. We could have done the same thing for any G covering, right? We can always, for any G covering of some anything else, right? We always have maps like this, okay? The only difference is that maybe this map is not an isomorphism, okay? So now I can explain the proof idea. So proof idea. I guess I wrote that earlier, so this is still the proof idea, okay? So now let's suppose that I have a contraction, meaning I have one of these diagrams that I explained earlier. So I have this A, and let's suppose that this covering can be reduced to something of smaller dimension. Okay, and I've written the arrows dotted because I said before in our definition previously we had to restrict to an open. So this will just be a birational map. Okay, and let's suppose this is a G cover. So our G cover on the left comes from a G cover on the right. Right? Well, so it's a G cover, and let's suppose the dimension of Y is less than G. Okay, so then we can use the construction that I just made above. So what do I have? So I have this map that I constructed above. So I have here I have an isomorphism with HG of AFP. Okay, and let me write this again. Now I remarked that this construction that we made here, this applies whenever I have a G cover, right? I didn't use anything here about abelian varieties, except at the very last stage. So I always have a map, right? So here I would also have a map to HG Y of FP. And then by functoriality, this diagram would commute by functoriality of the construction. Okay. Now, since we're in any case considering only birational covers, okay, I may as well assume I can always shrink Y, so I may assume Y is affine, but then HG Y of FP would be 0 because the cohomology of affines vanishes in degree above the dimension. Okay, and this would then give us a contradiction, right? Because on the one hand, we just showed, right? So we just showed this has to be 0. Oops. Okay, but on the other hand, so this map has to factor through 0 this way. On the other hand, it's an isomorphism that way. Right? Well, it gives a contradiction, almost. It doesn't give quite a contradiction yet. And the reason is I cheated, right? Because I told you at the beginning that these maps are only birational. Okay, so I really would have a diagram like this if these maps are honest maps. If these dotted maps are honest maps, then I really would have a diagram like this. And well, I would kind of get a contradiction in some sense if I could also choose Y to be affine, right? Because I said, well, these maps are only birational, so I may as well assume Y is affine, right? But then here I was somehow actually using that the maps are really well defined, okay? So I kind of cheated, okay? So what we really need to know is that you can make an argument like this when you replace A just by some open, okay? So what you really need to know is the following. 1 second. Okay, so almost, because H is birational. So this really would give a contradiction if we have the following proposition. that if I look at the image of HG of A, sorry, I'm switching between Z mod PZ and FP. So let me try to stick just to one. This is non-zero for U in A open. This is again under our conditions on P. Okay, so if I know that, you see, then I really get, I don't want to draw the diagram again, then I really would get a contradiction, because what I would really have here is U, right? And so since this is an isomorphism, if I then map this to the cohomology of U, and I know that the result is non-zero, then I would really get a contradiction.
Sorry,
Okay.
there is another question.
Yes.
By rational, do you mean really just the rational?
Oh, sorry. Yes, sorry. Yes. Sorry. That's what I mean. Sorry. Okay. Are there any other questions? Sorry, that was a horrible misspeaking.
Thank you.
Yeah. So I just have a rational map. It's to find some open in A. Are there any other questions? Okay. Good. Yeah. So, right. So really what I have, maybe I can just modify this diagram. So what we really have, because the map is rational, is not this, right? But actually just this map here. Okay. So I still get a contradiction, right? This is affine, so this is really zero. So this map would have to be zero, but this is an isomorphism. And so if I can show that the image of this guy is non-zero, then I'm in good shape. Okay. Okay. Good. So I want to make a couple of remarks about the statement. Okay. One, you can think it's worthwhile thinking about what kind of statement this is. So this is a statement somehow about the topology of like an open subset of a complex algebraic variety. But it's kind of a statement which is a little tricky, right? Because what this is saying is you have classes here. In the case of an abelian variety, all these classes just come from classes with Z coefficients, right? So this is saying when you map those Z classes to the Z classes in U, it's saying something like they don't become divisible by P, okay? And it's a statement which is a little bit subtle. The other thing is there's an analog with Q coefficients. Okay, so let me just write it here. So we can instead ask with Q coefficients, right? And there's a remark that this is an exercise to prove the analogous statement, the image is non-zero, is a consequence of Hodge theory. And the point is, in that case, and this is useful for what we'll see later, in that case, Hodge theory tells us that if we tensor this by C, okay, then I have the Hodge decomposition. And if I look at the G forms, this is actually direct summoned here, and I can look at the G forms also for U. Okay, and the point is that this map is non-zero, right? Because if I have a G form in A, it certainly restricts, well, it's non-zero, in fact, it's injective. It certainly restricts non-zero to every open subset, right? So that's why this map is non-zero. Okay, it's just for this reason. And the main reason I'm kind of showing you this is because the proof of this result, so this uses Hodge theory, the proof of the proposition will use some kind of p-adic Hodge theory, but in the end, it will reduce to a very similar looking statement. Okay. Okay, good. So now I'm going to...
Sorry,
Yes.
Just to clarify, I'm just trying to make sure that I have these quantifiers straight over here. So the idea is that you want to find a U, because like if U is affine,
No,
right? For all U, okay.
Yeah.
Okay. And wait, then maybe I'm just,
you could even
because if Y
formulate
has lower dimension, then if it's affine, it automatically disappears. But we want this for all open U. Okay, great.
Yeah. You could formulate this even with the generic point of the abelian variety. Okay, now I'm going to switch setup a little bit. So I'm always kind of moving these abelian varieties around. So what you have to believe is that you can go from one setup to the other setup. That's kind of more standard. So now let's switch setup. So A over K now will be an abelian variety over K over QP, and K over QP will be finite and unramified. And we're going to also assume that A has good reduction. Okay. And so then K has a ring of integers, and I'm going to put little k will be the residue field of big K. And I'm going to be looking at the ring of power series in one variable, which I'll call U over little k. And this is, of course, equipped with an absolute Frobenius. Okay. And so what I'm going to use is, this is a special case of the prismatic cohomology that was introduced by Bart and Scholze a couple of years ago. And I'm not going to tell you the definition. I'm going to tell you what the output is of this. Okay. So first of all, it gives a complex. It's a perfect complex of modules over this ring, this power series ring. And the magical thing about it is it kind of relates étale and Durham cohomology. Okay. So again, you can kind of keep this in mind, but I'm going to tell you how it relates them. Whoops, what happened? Okay. All right. I'm going to tell you how it relates them. So first of all, what I can do is if I look at this complex, and I tensor by the fraction field of my ring, okay, this is related to the étale cohomology of my abelian variety over the algebraic closure. Related means I didn't want to introduce more notation, but for our purposes, you can think that, well, related means that there's actually an isomorphism after tensoring by some big ring, right? So after tensoring by A inf, could just say, yeah, mod P. Okay, it doesn't really matter. The point is that, well, I'll tell you what you need from this, but for our purpose, you can think that they're essentially, that they're equal. It's not equal, it's only after tensoring by some ring, but that doesn't really matter for us. Okay. Okay, the second thing is the relationship with Durham cohomology. So this gamma, one of the structures it has is there's a semi-linear Frobenius on it. And if I pull it back by Frobenius, and then I tensor, I set U equal to 0. So I tensor by little k, so this U goes to 0. Then I get the mod P Durham cohomology of A naught. Sorry, of A naught here is the reduction of A mod P. So I'm using notation a little bit because I started with A in abelian variety over K, right? But I assumed it has good reduction. So I'm going to denote by the same symbol its model over OK, and then I have the reduction 1K, model little k, mod P rather. Okay. So So you should think that somehow at the I have this perfect complex over this over this ring, and at the generic point I have étale cohomology, and the special point I have de Rham cohomology. That's what you should be thinking. And then there's one more property. This is actually very important for the proof. That if I take now the cohomology of this, then, well, I know there's a Frobenius map because the whole complex is equipped. Such a thing. Okay. And the statement is that this Frobenius map can almost be inverted. Okay, so there exists a map here. So it can be inverted up to the multiplication by u to a power which is equal to the cohomological degree. And this is actually, it's this property that that's one of the places the restrictions on P comes from. I'll kind of explain that. I'll try to explain that if I have time. Okay, so now I can explain to you the proof of the proposition. Okay, so remember, what does the proposition say? It says that if I look at the image of this restriction map, oops. That this is non-zero. Okay, now if you see, it's very easy for me because I scroll down, so you can't see what the proposition said anymore. So I can just tell you it said this, right? In fact, of course, our original proposition, if we go back, that's when we were setting, that's before we switched setups, right? So we were over the complex numbers and we were working with topological cohomology. Now we're over in this kind of arithmetic situation. So we just work with the étale cohomology. But you should, of course, believe that this kind of statement implies the other one. Okay. So again, U is going to be open in A. So we want to show that the image of this is non-zero. Okay, so where U in A is open and dense. All right. One second. Yeah. So there's a little technical thing here, which is, which you can, I'm going to explain what it is, but if you like, you can ignore it. So U is it's open in A, so it's the complement of some Z in A closed. And what I can do is I can look at the abelian variety over OK. I can take the closure of Z, right? And so that's some open subset, and I can form its p-adic completion. And that's what I call U hat. So this is actually a formal scheme, and its generic fiber, in some sense, is contained in U. So I'm really going to be working with this U hat, but you can just imagine I'm working with U. It's not so important. That's just because the Spark-Schulze theory, it actually takes as an input smooth formal schemes over OK. And our Zariski open U isn't quite of this form. But in some sense, this thing I'm replacing it with is smaller. Okay. So, so the point is that if J is 0, if this image is 0, then a fortiori, this thing I'll call J hat, is 0. So, oops. So far, nothing really has happened. I mean, you can just ignore this step if you don't like it. Okay, so then this is 0. All right, now something will happen. So Now let's look at the following thing. So we want to use our prismatic cohomology. So we're going to look at J delta, J prism. This will be the image of the same thing that I considered before, but now for prismatic cohomology. So I'm going to look at the image of this guy. And here this is where I should put U hat, okay? It's funny, I told you could ignore the U hat, in my notes I actually did ignore it, okay? Now, the thing is, we know if we look at our property 1 back here, that at my prismatic cohomology, when I invert U, it's related to étale cohomology, okay? So I know that in étale cohomology, my map is 0, right? That's by assumption, okay? So I'm trying to get a contradiction. So I know this map is 0, okay? So by property 1, since J hat is 0, I get that J delta, when I invert U, must be 0, okay? So this tells me that J delta must be U torsion. So it's killed, every element is killed by some power of U. But now there's a lemma, and maybe I'll leave this lemma to the end if I have time, that actually J delta has no U torsion. This uses property 3. Remember our property, this property here. Okay, so if I have time, I'll explain that. But let's believe that for a second. Actually, I think looks like I will have time. All right. Anyway, let's finish the argument. So since J delta has no torsion, so I showed that, again, so the argument was this J hat is 0, that J delta, when I invert U, is related to J hat. So this tells me that when I invert U, the J delta becomes 0. Therefore, all the elements of U torsion. But in fact, this lemma says there is no U torsion. So I get that J delta is 0. Okay, but now I'm going to use 2. Remember, 2 was the relationship with Drahn cohomology. Okay, so by 2, this implies that if I look at the same thing for Drahn cohomology, that this is 0, right? Because from this J delta, we can get down to Drahn cohomology. Here, U naught is just a reduction. I'm not sure if I already said that, okay? But now we can use an argument very similar to the case of rational coefficients where we used Hodge theory, okay? So if I look at my map, sorry, I should use this actually. So I'm going to slightly change. Sorry. No, this is right. Okay, sorry. Right, sorry. So let's look at my map. Okay. So one of the rules of the game here is that you can analyze this mod P Drahn cohomology, and it has as a direct summand the G forms on the kind of the Frobenius pullback of A naught. So I just have absolute Frobenius on this field K, and I just pull back A naught by this Frobenius, right? And it turns out that there's something called the Cartier isomorphism. So you can show that this is a direct summand here, and that means you can use an argument just as in the rational case. Oops. Okay, that this can't be zero because it has a direct sum in this map, which involves restricting differentials on a Zariski open and characteristic P. Okay, so this is non-zero. It's not equal to zero. In fact, it's injective, right? So actually we prove something strong, and that's what we show in the paper, that this tells you that the image of this map actually is at least, so this guy has dimension G, this guy has, no, I guess, sorry, in this case, there's nothing stronger. So, so this map is injective, so you can see that this is non-zero, right? Okay, so this gives a contradiction, right? So we started with kind of something in natal cohomology. We used it to show this J delta. This J delta was also zero, and then we specialized to the mod P de Rham cohomology, and we showed that implied the corresponding thing there was zero, but there you can compute the thing with differentials and see that it's non-zero. Okay, so are there any questions? So I do have time to give this lemma that J delta has no torsion. Where was the lemma? The lemma was, yeah, here, this lemma. Okay, so the proof of the lemma is kind of cute. It doesn't use anything except the property 3. Okay, so proof of lemma. There's no U torsion, but this is nice because at least you see where the condition on P arises. Okay, so the point is, if you remember property 3, sorry for scrolling back all the time, but I want you to remember what this diagram looks like. Okay, there's such a thing when I apply it to A, but also when I apply it to this U hat. Okay, so because all the constructions are functorial, what I get is the corresponding diagram also for J delta. So the diagram looks like this. So it has a Frobenius, and then there's an inverse up to U to the I. Okay. And now here's the argument. So remember, J delta was the image of this map, right? And here I started with some cohomology, and this is a finitely generated module over my power series ring in U. So J delta is a finitely generated module. Okay, so if there's any torsion, any U torsion, there's some integer there's some power of U which kills all the U torsion. Okay, so let me look at that integer. Okay, so there exists. So there exists a smallest integer M and C such that U to the mj delta is 0. All right. Good. And now let's choose some element such that U to the m minus 1 times x is not equal to 0. Okay. So now let me look at the element 1 tensor x inside the pullback by Frobenius on this guy, right? So my Frobenius is the map here given by u goes to the u to the p. And this is a finite flat map, okay? So it's easy to see, just because of the structure theory of modules, finitely generated modules over this thing, that for this element, the power of p, the power of u that I need to kill it, okay, is exactly gets multiplied by p when I do this Frobenius pullback. So this means that this is 0, but if I drop the power by 1, this is not 0. Okay. And now what we do is I just look at the sequence of maps that I had before. Okay, so the composite is u to the I. I guess I will be equal to g in the application, but let's do it this way. Oops. Right. Just 1 second. Yeah. So yeah, let's do the following thing. Right. So I'm going to consider in here the element tensor x. Okay. So this is a linear map. So this gets mapped to times x, which is 0. And then the composite is just ui plus m tensor x. Okay. So what's the point of looking at this map, which I already know is 0? I set it up to be that way. Okay. Well, I know this guy can't be 0 unless the exponent here is at least p times m. So that tells me that I plus m is greater or equal to p times m, which gives me that p is less than or equal to 1 I plus m, which I guess is less than or equal to 1 plus I. And in the application, we'll take I equal to bg. Okay, so, but we assumed p is at least g plus 2. Okay, so basically, I mean, this kind of structure, if you have a module, the point is if you have a finitely generated module over this k double brackets u, then when you have this kind of structure, okay, it actually, if p is not too small, compared to like this exponent here, it actually shows you can't have any u torsion for a kind of for elementary reasons. Okay, so I did the calculation for you. But okay, good. So let me stop there.
Hey, thanks for your excellent talk. Any questions?
Okay, I have a question, but there's one question in the chat. Maybe I can ask later.
Is the conjecture on the general electrical equation? Yes, it's known for n equals 5. Yes, I think it is related to that. Is it related to unsolvability by radicals? Yes.
Okay, so the only, if I understand correctly, the only place you use the fact that A is an abelian variety is the isomorphism between the degree G cohomology and the wedge G, right?
Right. So what you're using, right. So yes. So you're using, let me go back here, all the way back here. Right. So this is kind of a very general strategy, right? But what you're using is that all the classes come from the classes of this covering group G. Okay. So we didn't have to do it like this, right? We could have just looked at I didn't phrase it this way, but you could just look at the cohomology of this finite group G, okay? And always gives rise to cohomology in here. But in general, that map might not be surjective, right?
So as soon as it's surjective, then you get similar results, right?
Right, but that's kind of, but that's a strong condition. And in fact, here it's very nice because this HG is even a wedge of the H1s, right? But for example, when I gave this statement for a product of curves, right? So in general, that condition is kind of unreasonably strong, and it's kind of often hard to check that a lot of the time it's not true, but even when it is true, it's hard to check that the Hg of G maps onto the Hg of your variety. But what you can do is you can always make an argument where instead of just looking at Hg, you actually just look at the top wedge of the H1. Okay, and then you can run this whole argument with the J delta and the prismatic cohomology just for kind of the image of the top wedge of the H1. And that still works, and that gives quite a general result about these P homology covers. So the covers whose group is an elementary abelian P group.
Okay, so this somehow shows that this is not very it's not a very arithmetic result, right? It's more topological, as you mentioned somehow.
The statement, yes, the statement is topological. That's right. Yeah.
Okay, and can you explain why you were interested in this result, this question?
Well, I mean, Benson and Jesse have like this long collaboration on these kind of questions. I mean, you know, they're very classical questions. So I think they kind of justify they justify themselves.
Okay.
There's no like further application of this that I know of. That's the question.
Great, thank you very much.
Sorry, there is another question in the chat box that says, do you actually need the prismatic cohomology? Oh, okay.
Right, that's a good question. So when I was thinking about this, I thought about that, and I didn't immediately try to use prismatic cohomology. I tried to use, for example, these results of faultings, but I couldn't make that work. So in the end, I as far as I can tell, you really need prismatic cohomology. And in fact, you really need prismatic cohomology. For the experts, let me just say that you might ask, do you need prismatic cohomology, or is this A-inf cohomology enough, right? But you see this argument, now I'm glad I gave this argument at the end, this one right at the end with the U torsion. This really uses that you're over this ring, which is a discrete valuation ring, right? And that you can talk about, you know, the biggest power, the smallest power of U, which kills an element. This wouldn't work if you were just working in like A-inf mod P. So I don't know of any other proof which doesn't use this theory. Is it possible to axiomatic properties? Yeah, I mean, in some sense, I did this, right? I don't know how general you want to think of like a proof which works, but what I told you here, just the properties which are needed to make it work. So one, lets you compare your theory with étale cohomology, is what you're interested in, right? Two allows you to like reduce to a question in de Rham cohomology, and three helps you make the reduction, kind of. So you have these two cohomology theories sitting at the two fibers of this discrete valuation ring. So it seems to just have the minimal amount of information. Yeah, this I can't. I can't pause this question. I mean, number theoretic counterpart. Yeah, it sounds interesting, but I don't know.
I have two more questions, sorry.
Mm-hmm.
So, do you think it would be possible to get a better bound on P if you change your prism instead of using K double bracket U?
Well, the thing is, in the actual paper, there are a couple of places, depending on exactly which theorem you're trying to prove. There are, I think, at least 3 or maybe 4 places where the bounds on P show up. In this particular example, with abelian varieties, I think this is the only place where the bound shows up. But the place it comes from is, this is what's called the isogeny property for prismatic cohomology. And it really comes from this exponent, from the fact that you can get an inverse here up to U to the power of the u to the power of the uniformizer, and that doesn't depend on the prism. I mean, somehow that's one of the rules of the game. For like, if you have any prism, then the isogeny property tells you this, but the exponent here is really the degree, your cohomological degree.
But
right?
the action of, but the action of phi, I'm not sure, but
I see. No. But see, we're in characteristic P, right? We're just working in characteristic P. So
but you goes to use the P, right?
Sorry?
But you choose the Frobenius that sends you to use the P, but if you choose some other prism, I mean.
No, but I mean, the Frobenius we're in characteristic P. So Frobenius will send you to the P always.
I mean, I think maybe I'm confused, but I think you chose this prism, which is in characteristic P, but you could.
Oh, no, but the fact that we're in characteristic P, just there's nothing to be gained because we're just considering cohomology in characteristic P, right? So, I mean, I guess if you could consider, that's just, I chose like the covering that's given by multiplication by P, right, on the abelian variety. And that's why I'm only considering FP coefficients. I could, of course, maybe I could consider the covering that's given by multiplication by P squared, right? Then I could try to do this analysis with P squared, Z mod P squared, right? And then maybe the choice of prism would matter. I didn't think about this. I mean, of course, when you can get, the reason I formulate that way is because when you can get a result for the mod P cover, the one given by multiplication by P, if you can show that's incompressible, then of course the one for P squared is also incompressible.
And so maybe my last question is, I'm sorry. So if instead of using abelian varieties, I pick I don't know, a Greenfield module, I think one that still has this relation between the red G cohomology and the VG cohomology.
Can you say again what?
I mean, if you instead of working with abelian varieties, one works with Greenfield modules.
Oh, I never thought about this. Yeah, I don't know.
Thank you.
Yes. So the question is, do you need some assumptions when you embed like at this last step? Yes, you need some degeneration of the Hodge-Durham spectral sequence on the E1 page. That's really for A. That's really for more for A. I mean, it holds in this situation, but that's really more for A than for U naught, right? Actually, if U naught is small enough, then the whole Hodge, I mean, all the pieces of the Hodge-Durham, it's actually not the Hodge-Durham, but the conjugate spectral sequence here, because I have this Frobenius twist, and all the other pieces actually disappear once U naught is affine. Other questions?
Yeah, I guess, I mean, it seems like now I see my original question about characteristic prime to P. Sort of the problem is that, I mean, if you're using prismatic cohomology, it's something fundamentally p-adic. You don't really have kind of two different characteristics involved. Is there any way of getting some kind of like squishy statement about it working for, you know, some large number of prime to P characteristics, even though you can't actually identify any of them by doing some kind of like ultra product argument or something like that?
That's a great question. I mean, I like the question because without addressing like that, because I have nothing, I never thought about it. So, but I like the question because there's a nice tension there, right? Like usually, so if you ask the question when the characteristic is P, like maybe it works, maybe it doesn't, but you somehow have the feeling that, you know, whatever
it's a different question.
It's a different question, right? Yeah. But when the characteristic eval is not equal to P, then you have the feeling that things should work the same way, like for general principles, but the proof really doesn't work. So that's a challenge. I don't know about this ultra product argument. I would want to find just an argument that actually works.
Okay.
Yeah.
And I mean, maybe one other just kind of silly question. I just want to make sure, was the wool pulled over our eyes at any point in this proof, or is it really like, given prismatic cohomology is a black box, is this really all the significant steps of the argument?
These are all the significant steps of the argument.
Okay, great.
Yeah. The only thing I didn't discuss in detail is like here, but there was a question about this, that here to do this, you kind of, in general, in the general theorem, you have to also kind of, but this is a condition on P, you have to make sure like the conjugate spectral sequence degenerates so that this is a direct sum. And so there are some things, the only place I would say the wool is slightly pulverized is that there's a general theorem with some conditions, which applies more generally than just for abelian varieties.
Mm-hmm.
And in that case, there are some of the steps here become, you have to be a little bit more careful. But for abelian varieties, this is really the proof.
Gotcha. Great. Thank you.
L. Can you, sorry.
Sorry, I can hear you now, but I couldn't hear you just a second ago. Is someone trying to say something or?
Okay, is it better? Can you hear me?
Yes, now I can hear you, yes.
So suppose you're in characteristic L and you want a similar statement with, let's say, QP coefficients. And so is like, you know, at least in ORC, there's a simple Hodge theory argument. Is there a simple argument there?
Yeah, this is also a great question. I don't know. I think for abelian varieties, maybe I'd want the abelian varieties, you can always lift them, right? Sure. So maybe that's for abelian varieties, maybe that's like the easiest way to make the argument. I'm not saying I see the argument. I'm just saying maybe that's like one thing you could try. Yeah, but even that's right. I don't know any argument other than Hodge theory. So for rational coefficients. So that's also, yeah, I don't know.
Thank you. Thanks a lot.
Any other questions?
I'm not, first of all, I'm not 100% sure, or I feel somewhat lost regarding when you're speaking of where the characteristic appears in different places. And is the idea that they need to match when it's the coefficients in the cohomology versus when it's describes either the Frobenius map or the map on the abelian variety. Those two parameters need to match. Is that what was being said? And otherwise, the whole argument wouldn't work, and they do really.
That's right. That's right. That's right. So So that's right. So let me just repeat what you just said. So I think you're what you're saying is exactly right. So you start with that. Yes. Sorry.
And yeah, let's do that, and then I'll ask something else. But I don't know where to do. But the second question is, I mean, is there any other place in the whole literature where those two things wouldn't match, and that creates sort of a interesting sets or series of questions that this is a particular instance of that generalization? That's the second question.
You mean where they don't match or where they do match?
Yeah, when they don't match. Or is the case when they don't match completely ignores everywhere else too?
You mean like these questions we had about how do you do this in characteristic L different from P, for example?
Yeah, exactly.
Yeah. Right. Yeah, I don't. Probably that's always. Someone, you should mute yourself.
Yes.
Sorry. Do you want me to answer? You should mute yourself because I think there's some background noise.
Yeah, sorry. There is some, I mean, yeah, I can't prevent it too much because I have to be here for a little while. That's why I was
okay, but you can mute yourself, right? Or the
okay, yes.
Or the host can mute you. It's just it's hard to answer the question of those. So yeah, so what you're so I think that's probably always an issue. These L not equal to P questions are tricky. But what you said before is kind of exactly right. That somehow that's the theme, that you have a question in topology, which involves something like, that's what I said at the beginning, you're kind of restricting these cohomology classes, and you're saying they don't all become divisible by P in the on the Zariski open. So initially the characteristic is showing up in the coefficients of your cohomology, and then you kind of switch it to a question in where the geometry is happening in characteristic P. Originally, the geometry is in characteristic 0, the coefficients in characteristic P, and then you make the geometry in characteristic P as well. That allows you to reduce to a statement about differentials. Yeah, this L not equal to P thing I'd never thought about before, but I'm definitely kind of inspired by the questions in this talk to do so.
Well, thank you.
Who is in charge of this talk?
What was
any question? It seems there is no question. Thanks again for your great talk, and let's me to encourage. Really was a great honor for us to have Professor Mark Kisin as one of our speakers. Thanks again, and thanks Ali Rajai for organizing this seminar. And I should mention that the next our speaker is Reza Taleb from Shahid Behesht University in 2 weeks from now. So I will start this recording.